Yeah. Once again, the next talk is by Mohamed Mhamdi from Tunisia. The title is Hölder Continuity of Generalized Harmonic Functions in the Unit Disk. You can start your presentation.
Before we study this talk, I would like to take a moment to express my heartfelt gratitude for the exceptional committee responsible of organizing and orchestrating this outstanding event. Today, I will talk about the Hölder continuity of generalized harmonic function in the unit disk. Actually, I will talk about the membership Hölder classes of PQ harmonic functions such that their boundaries function are Hölder continuous of order beta. Let us begin by this definition. Let E be a subset, bounded subset of the complex plane C, and omega be a measurement that is a continuous increasing function on 0 T0, where T0 is large enough and satisfy omega 0, and omega T over T is more increasing. We see that F has a modulus of continuity omega, where omega is a measurement. And we write F in big lambda indexed by omega if there is a constant C, positive C, such that we have this inequality. And we see that F is beta Hölder continuous on E, and we write F in lambda indexed by beta when omega T written as T power beta. So we obtain this inequality. In the particular case, when beta equals 1, we call that F is Lipschitz continuous. Let's begin by these results proved by Diakonov and Hölder and Oberlein. Prove that when the boundaries function is Hölder continuity on the unit circle with exponent beta, with beta between 0 and 1. This implies that the harmonic extension is also Hölder continuous. But for the particular case when beta equals 1, that is the Lipschitz continuity. When F, the boundary function F, is Lipschitz continuously in the unit circle, does not imply that the harmonic extension is Lipschitz continuity. After that, with an extra condition, Arzonovich and his collaborators proved the following results. When F is Lipschitz continuous on the unit circle and its harmonic extension is Kakazi irregular, then it keeps it Lipschitz continuous on the unit disk. And we see the following observation. When beta between 0 and 1, we have U, beta Hölder continuous on the unit disk, implies that the boundary function F is beta Hölder continuous on the unit circle. Now let us define the harmonic, the generalized harmonic function, which is called alpha harmonic function. Let alpha bigger than -1, and we say that U is alpha harmonic on the unit disk. When U satisfies the following equation, delta alpha of U equals 0 on the unit disk, where delta alpha is a second order differential operator. Here dz and d bar z as presented as a linear combination of dx and dy. We remark that d0 is the classical Laplacian, hence zero harmonic function is a classical harmonic function, and the function p indexed by alpha of f, which is the product, the Ritz product, is alpha harmonic. That is a solution of the following equation, and here f is a continuous function on the unit circle, which is the boundary of the unit disk. In the case when beta equals 1, Lee and Wong in 2019 proved that when alpha bigger than -1, For the first case, if alpha is positive and f is Lipschitz continuous on the unit circle, then the alpha harmonic extension, it keep it Lipschitz continuous on the unit disk. But for alpha is negative, there exists a function f Lipschitz continuous on the unit circle such that the p alpha of f is not. Next, Olofsson proved the following. When alpha bigger than -1 and beta between 0 and 1, f beta Hölder continues on the unit circle, and u is alpha harmonic function with the boundary function f. If we have these two cases, if beta is less than alpha plus 1, then u is beta Hölder continues on the unit disk. And if beta is bigger than alpha plus 1, then u is beta Hölder continues on the unit disk if and only if the transform Fourier of f of n is 0 when n is negative, if and only if u is analytic on the unit disk. So as an extended results of the previous theorems, our investigation involves around the on-night circle. Let us define the PQ harmonic function, which is a generalized harmonic function. We say that u is PQ harmonic if u is twice continuously differentiable in disk and u satisfying LPQ of u equals 0, where LPQ is a second order differentiable operator. PQ are real parameters. We remark that if PQ equals q equals 0, the solution u is the classical harmonic function. Here, 0 alpha harmonic function are alpha harmonic functions. This class of generalized harmonic function have previously been studied in the higher dimension by Arendt and his collaborators in 1996. Now let us consider the directly boundary value problem. U is LPQ harmonic on the unit disk and equal a continuous function on the unit circle. F. Klimberg and Olofsson give the form of the solution of the equation 1 when PQ are in R over minus the negative integer, such that P plus Q bigger than -1, and U is PQ harmonic function on the unit disks, satisfying the Dirichlet problem, the following problem. Then you have the following Poisson type integral. Here, KPQ is a kernel defined with this expansion, and CPQ is chosen as a factor of normalization in order to the quantity MPQ, which equal KPQ of 1. Here we replace F by 1. We obtain the quantity MPQ. This quantity tends to 1 when modulo Z tends to 1. That is, Z tends to the boundary. After that, Gehring and Marciu proved the following results. When they estimated the sum of partial derivative and they obtained this type of inequality with alpha between 0 and 1 and C a positive constant, then U is alpha Hölder continues on the unit disk. Sorry. After that, Pavlovich gives an extended results of results Gehring and Marciu. When F is continuously differentiable and omega B imagine satisfying the Dini condition, that is omega 1, which equals the integral between 0 and 1, omega T over T is bounded. If F satisfies this inequality, that is the sum of partial derivative less than constant times omega of 1 minus modulus of z square over 1 minus modulus of z square, then F has a modulus of continuity omega 1 on the unit disk. So our task is to estimate the sum of partial derivative of PQ harmonic function, and then we obtain the following result. When P plus Q bigger than minus 1 and beta between 0 and 1, is plus the condition is PQ harmonic function. Then we obtain the following estimates of the partial derivatives. In the critical case, when P plus Q equals beta minus 1, we obtain the following result. When P plus Q between minus 1 and 0, and beta between 0 and 1, such that P plus Q equal beta minus 1. Here we choose P plus Q is negative 0 and minus 1, between minus 1 and 0, because beta is between 0 and 1. So P plus Q is negative. Also, we take F is beta Hölder continues on the unit circle, and U is PQ harmonic function on the unit disk. Then the sum of the partial derivative are less than the following quantity. So as an application of the results Gehring and Marcio and Pavlovich, we obtain the first main result of this talk. When P plus Q bigger than minus 1 and beta between 0 and 1, F beta Hölder continues on the unit circle, and U is PQ harmonic function. It tells that if P plus Q bigger than beta minus 1, then U is keep it beta Hölder continues on the unit disk. But here, for P plus Q between minus 1 and beta minus 1, U is not beta Hölder continuous as the boundary function, but U is Hölder continuous of order P plus Q plus 1 on the unit disk. And in the critical case, when P plus Q equals beta minus 1, then U has a modulus of continuity omega indexed by beta, where omega indexed by beta is as follows. And when we estimate this quantity, the function omega indexed by beta of t, by t power alpha, we obtain this particular case. That is, U is in the intersection of all space big lambda indexed by alpha in the unit disk, and alpha bit is between 0 and 1. As a corollary, in the case when beta equals 1, the Lipschitz, that is the Lipschitz continuity of the boundary function on the unit circle, and U is PQ harmonic function. It tells that if P plus Q is positive, then U is keep it Lipschitz continues on the unit disk. But when P plus Q between minus 1 and 0, then U is Hölder continues of order P plus Q plus 1 on the unit disk. And also we have the critical case if P plus Q is equal to 0. We have the following condition: U has a modulus of continuity omega, and we have this particular case U in the intersection of all lambda alpha in the unit disk, where alpha here between 0 and 1 strict. Now we provide an example when the function f is Lipschitz continues on the unit circle. When P plus Q is negative, we get a function U is not Lipschitz on the unit disk. So we give these two cases when P plus Q is between minus 1 and 0, and K is a relative integer. We have this function which equal a constant times a Gaussian hypergeometric function. And in the case when P plus Q equals 0, we get this function U0, which equal a constant CPQ times Gaussian hypergeometric function as follows. Through these two cases, we can prove that one of the partial derivatives of uk respectively, u0, is not bounded, which yields that both uk and u0 is not Lipschitz continuous on the unit disk. Now let's move to the second main result of this talk. When we add extra condition quasi-conform, we obtain the following results. Let us recall the sense preserving diffeomorphism U is said to be quasi-conform if we have this inequality. Then we obtain the following result. When beta between 0 and 1 and p plus q bigger than -1 and f is Hölder continuous on the unit circle and u is pq harmonic function, be a quasi-conformal, then without any case we have u is beta Hölder continuous on the unit disk. With this condition, when f is Lipschitz continuous on the unit circle, this implies u also is Lipschitz continuous on the unit disk. That is, the quasi-conformal ensure the Lipschitz continuous from the boundary circle to the disk, to the disk, yes. And we remark finally, we remark that if beta 1 is less than beta 2, then the set lambda beta 2 is a subset of lambda beta 1. That is the set lambda beta are nested. In the case p plus q between -1 and beta -1, the function pq harmonic function, the pq harmonic function belongs to the larger Hölder space of than f. In the previous theorem, we provide that being quasi-conformal is sufficient to ensure the stability of Hölder spaces. And as a perspective, it will be interesting to find necessary and sufficient condition on F to get such stability as done by Olofsson. This is a list of few references. And thank you for your attention.